Okay, let's get started. I am remembering to pass around the attendance sheet today, so make sure you sign it and pass it along. We're going to spend today finishing off the first of our 6 themes, an introduction to evolutionary robotics. We're going to conclude lecture 3 today, our discussion of this idea of embodied cognition, this idea of embodiment which sort of divides all the approaches to trying to make intelligent machines into these two groups. We will then start our second theme of the course, the tools of the trade, which you have already started to work on. We'll talk today about artificial neural networks. Again, we're just going to do a very surface treatment of artificial neural networks. We're going to learn just enough to be able to place them into our robots to enable our robots to behave in PyroSim. We may get all of the way through lecture 4 today. We'll see how we do. I haven't posted the individual slide deck for lecture 5, so if we start that today, not to worry, I'll post lecture 5 slides right after class today. Okay, any remaining installation issues with PyroSim? I don't see any hands. That's fantastic news. That's great. While we're on the topic of PyroSim, for those of you that are on a Windows machine and are using the USB drive, as you know, you're running Linux off of the USB drive, and unless you set it up, you don't have Wi-Fi access, so it's a little bit tricky to upload your screenshots to the web. So you can either take a picture of your screen with your phone, or I've added some additional instructions to the simulation project. So if you go back to simulation and you go down to instruction number 16, which is where you upload your first screenshot, I've added a little video here that will show you how to actually store screenshots that you take onto the USB drive. So you store the screenshots onto the USB drive, pull it out, restart your machine, boot it up in Windows, plug the USB drive back in, and you can access your screenshots on there. If that's easier for you rather than taking a picture with your phone, that's fine. As I mentioned, when we're grading your assignments, we're not looking for cinematic quality, so even if the things are a little shaky or a little blurry, as long as we can see what we're looking for, that's perfectly fine. All good? Okay, so just a reminder, undergraduates, you are working on assignment 2 where you're going to be implementing the objects that make up your robot. And then in the second sub-assignment, assignment 2B, you're going to be adding joints which connect pairs of objects together. Joints can be a little bit tricky because unlike objects, you don't see them visually in the simulation. So spend some time making sure you understand what joints are. They need to be located at the intersection of 2 objects. So if I'm trying to add an elbow joint, I've got my lower arm and my upper arm, and I want to make sure the position of the joint is here. And you're then going to be defining a joint normal, which you can think of as a vector which points outward from the position of the joint. And that joint normal, that normal vector, defines a plane which is normal to the vector. And the 2 objects that are connected by the joint are going to rotate through the plane defined by the normal vector. Make sense? Okay. Okay, so let's jump back then to lecture. We're working our way through lecture 3 on embodied cognition. And to try and illustrate what this idea of embodied cognition is, we're going to touch on a number of building blocks of intelligence, and we're going to look at non-embodied approaches to building that building block into machines, non-embodied approaches and embodied approaches. We started with pattern recognition last time. Non-embodied approach, like a deep learner, takes as input an image of Marilyn Monroe and tries to find Marilyn in the photograph. We then looked at BabyBot, which has a body and can push against the world and observe how the world pushes back. And we saw how BabyBot starts to learn about objects in its world. I then moved us on to the next building block of intelligence, planning. Deep Blue is a good example of a non-embodied planner. Somebody types in the state of the chessboard, and Deep Blue plans its moves and possible counter moves by Kasparov, and then moves to counter those moves and so on, right? Planning into the future and then deciding on a course of action which will maximize Deep Blue's chance of winning. Before we got to the embodied approach to planning, we took a little bit of a diversion at the end of class last time by starting to look at a third building block of intelligence, which is probably the most controversial of all, free will. And we started to look at not a robotics experiment, but a neuroscience experiment where we have these human subjects. They're watching a clock. There's a red dot moving around the clock. The human subjects are asked to decide of their own free will at a certain point in time to move their finger. They're asked to be honest and actually move their finger at the moment they make that decision, and then report back to the investigators the moment in time that they had made the decision. That moment in time is shown here, and 200 milliseconds after that point in time, for all the human subjects, most of all the other human subjects, the investigators would see that the EMG lit up, that the finger actually moved, so it seemed that the human subjects were being honest. At the moment that the human subjects reported that they had made the decision to move their finger, there was a characteristic pattern in their EEG, and that pattern was only there at that point in time. It disappeared after, and it also did not exist back here. So it seemed to be that there was some EEG pattern, and it might be different for different human subjects, but that pattern always showed up at the moment that they had made the decision to move their finger. So far, so good. Did you have a question?
No, maybe you're getting to it, but I know last class you said that it seemed like the decision had already been made, like, I don't know, like several...
300 milliseconds earlier,
now,
right.
Is it possible that that's just because by the time that, that thought is formed in your brain and you think that, is it possible that the process...
Took that long.
Well, because like maybe you at the negative you had formed that thought, but whatever, you have to sort of form that thought in your brain. I don't know. So I guess I'm just trying to say is like, is it possible that that was really thinking that, but it's just it takes like a little bit longer for that to sort of out?
That's exactly the conclusion that you draw from the data. That the decision seemed to have actually been made at this point in time. And it took 300 milliseconds to reach this point where the human subject thought they had made the decision. This was the point in time that the subject said, I made the decision at this time. Right? But unbeknownst to the human subject, another part of their brain, now whether that's them or not, that's up for you to decide, seemed to have made the decision. Or at least the movement of the finger was associated 500 milliseconds later with this EEG pattern. There are lots of different ways to interpret the Libet data. I'm not trying to convince you that you do or don't have free will. You can make that decision on your own if you're free to make decisions. The point we're making for our purposes is at the top there. Thinking about thinking is misleading. Right? If you introspect, if you watch yourself going about your daily routine, you can watch yourself making decisions. I'm going to get lunch before class. No, I'm going to get lunch after class. You make decisions all the time of your own free will. It seems obvious that that's what you're doing when you introspect. But when we actually look more deeply or more carefully about what's going on inside a nervous system, it doesn't seem to line up sometimes with our understanding, with our introspection. So thinking about thinking is misleading, and introspection can often be dangerous. Hopefully, when I showed you the picture of Marilyn here, you recognized her almost instantaneously. It's super easy, right? It's trivial for us to recognize familiar faces, right? Shouldn't take too long to get a machine to do that. If we went back to 1956, it should take us about 6 weeks, right? Over the summer, we'll figure this out. It's easy. I introspect. I watch myself recognizing Marilyn. It's quick, it's easy, it's painless, no problem, right? Clearly, if I can do it so easy, it might take a little bit longer, but we'll get a machine to do it. Part of the problem in AI is exactly that, is the thing that we are trying to build into these machines is the thing that we're most comfortable with, or the thing that's most familiar to us, our own behavior. You're observing your own behavior all the time and drawing conclusions about how you do it, how easy it is, and so on. And it turns out often it's not as easy as we thought, or at least so far it hasn't been as easy to boil down exactly what decision making is, or planning is, or pattern recognition is. It's been hard to define these things clearly and build them into machines. Okay, so as we continue on in the course, we're going to look at some of these, we're going to look at some evolved robots that are doing things that look like decision making and planning and pattern recognition. And we're going to open up these robots like we did with the Bratenberg vehicles and look inside. And often the way that they're doing it seems strange to us. It doesn't look like the way that we think we do it. Okay, so keep that in mind. Thinking about thinking can be misleading. Okay, so let's come back to planning. We looked at the non-embodied approach to planning. Deep Blue, it builds this decision tree or this game tree. Maybe I'll make these moves, then Kasparov will make these moves, then I will make these moves in response. Let's have a look now at Shaky the robot. So this is also part of our history of AI here. Shaky was one of the first autonomous machines. There's no cables going into Shaky here. Shaky is all on his own, moving about in a room at the Stanford Research Institute in the late 60s and early 70s. Shaky had an onboard computer. This was state-of-the-art in the 1960s. This was already pretty amazing. Shaky also has television camera and rangefinder in its head, so it can sort of scan the room around itself. It would be placed in a room with various obstacles and then be asked to move to a point in the room or to find the door and leave the room. It would be given some task to do. And Shaky would plan how to do that. So sitting at its current location, first of all, in the top right there, Shaky would use its camera and laser rangefinder to scan the room or sense the room. Shaky would then build a model of its environment. That's a screenshot from PyroSim, so that didn't exist back in the 60s. Shaky had some other sort of modeling software, but it would basically create a virtual world on board. Again, pretty amazing for this time. So it had a model, this internal representation of the world. Inside that model, it would then plan an escape route. So how is it going to get out of the room? It wouldn't execute that entire black trajectory there. It would just move a short distance along that trajectory and then stop, sense again, update the model, move, sense, model, plan, move, sense, model, plan, move. So you can now probably figure out why Shaky the robot is called Shaky the robot. It would do that, and then 2 minutes later it would do that. And if you were exceedingly patient, after about 12 hours, Shaky would finally make its way out of the room, right? Okay, you're laughing now, but again, this is 1960s computer technology all on board. Pretty good for that time. So why did Shaky only move a short distance along its trajectory? Why didn't it plan a trajectory and then carry it out and get out of the room? Why did it pause every once in a while and update its model?
To see if there was something in the way.
They say if there was something in the way or something had changed, right? So as Shaky is moving, it's not able to really update the model, right? It couldn't do all these things at once, so it would move a little bit, look to see if things had changed, update, move, and so on, right? Now we have autonomous drones, which are moving all the time and modeling, but it is still tricky for a drone to update a detailed model as it goes. The nice thing about drones is they're in the air and there aren't that many obstacles, so it can get away with moving a fair distance before updating its models. But this is still a challenge even with state-of-the-art modern-day technology, is that in order to plan and move about in a complex world that has lots of obstacles and is always changing, we need to sense, model, plan, and then act. This should sound familiar to you. This is not that different from a Turing machine, which is sensing the symbol on the tape, reading that symbol in, doing some computation, deciding what to do next, How to move, which might be to move the tape forward or back or write a symbol on the tape, right? So we're still sort of have this traditional paradigm of machines which are sensing, thinking, and acting, which works okay, but not if you need to do this very quickly in a constantly changing world. It feels to you like you sense, you think, and then you act, right? So obviously that's how we should build machines. But is that actually what we're doing? In the 1980s, Rod Brooks, a researcher at MIT, introduced a very different approach that demolished this sense, think, plan, act paradigm. So instead of doing everything one after the other, we're going to do everything in parallel. So this is like a neural network, which also does everything in parallel. But it focuses mostly on behavior. So if we have intelligent machines that have bodies and they're trying to move about in the world, they're going to have to react very, very quickly to things that are going on in their environment. How can we make sure that they do that? Well, one way to do that is to build up what became known as the subsumption architecture. We'll describe this in detail here. Most important thing about subsumption architecture is, again, everything is arranged in parallel. But the robot is not doing a whole bunch of things in parallel. It's still only doing one thing at a time. How does this work? Well, we're going to organize in layers, starting from the bottom going up to the top, things that are most urgent or most important. Okay, we have possibly a very expensive robot, and if it's moving around quickly, the thing we want least to happen is for it to collide with an object. So object avoidance is the most important thing. So we have obstacle sensors. And if the obstacle sensors report that there is an obstacle close by, that signal from the obstacle sensor says the most important behavior right now is avoid obstacles. So imagine you have obstacle sensors. And like in the Bratenberg vehicle, where we have two sensors connected to two wheels, if those sensors report that there's an obstacle nearby, they take over control of the motors. So immediately the robot forgets about everything else and just pays attention to avoiding obstacles. Okay. If there are not obstacles nearby, then this sort of system relaxes a little bit, and other systems can subsume or take over control of the motors. So metaphorically, the obstacle sensors kind of relax their grip on the motors, and if suddenly the audio sensors report a loud noise off to the right, the audio sensors might say, this is important, not as important as avoiding obstacles, but still important, turn away from the loud noise. If there are no obstacles nearby and no loud noises, then the light sensors are free to control the motors. They subsume control of the motors, and it will turn towards the light. This is basically the aggressor Bratenberg vehicle, right? So it's attracted to light, scared of loud sounds. If there's no clear light source, there's no loud sounds, there's no obstacles, no danger, there's nothing really interesting going on right now. So let's just explore the environment. Let's move around. Okay, so at every point in time in a subsumption architecture, there is a direct connection from sensors to the motors. The machine is never sitting still, like Shaky the robot. The motors are always in motion. The robot is always moving, but how it's moving and what stimuli it's responding to can change from moment to moment depending on the urgency or the priority of these sensors. It makes sense once you think about it, but it's harder to think about what this robot does. What if there's a medium sound and a light source and an obstacle that's kind of close? It's hard for us to think about what the robot would do in that situation. This approach is somewhat less intuitive to us, or at least for most of us, than this one. When we think about moving around in our world, it feels more like we're doing this. It's the end of class, I've packed up all my notes, this door is slightly closer than this one, I finished planning, so I'm going to go that way, right? Feels like that's what I'm doing, but maybe what we're doing is closer to this. Or maybe what we're actually doing is something completely different. Anyways, this one makes a lot more sense for robots because they're continuously in motion and continuously responding to changes in their environment. This subsumption architecture was worked out in the 1980s and actually now is built into the most successful commercial robot out there. Some of you may have one at home. What robot am I talking about?
Roomba.
The Roomba, absolutely. So Rod Brooks quit his job at MIT and went to found the iRobot company, and their first commercially successful product was Roomba, which has a version of this inside. What is important to Roomba? You can make a loud sound near Roomba and it doesn't react to sound, doesn't care much about that.
Mostly just avoiding obstacles.
Avoiding obstacles, especially going off the top of stairs, right? So explore or move around at random. So exploration controls the motors until the obstacle sensors sense an obstacle or the ground in front of the robot drops away because it's on the lip of the top of the stairs. Then the obstacle sensors control what the motors do. It turns around away from a sensor, it turns away from an obstacle. Now there's no obstacles in front of it. And exploration again subsumes the motors. Right? Pretty simple idea and turns out to be very useful for the Roomba. Be much better to have that than something like this where the Roomba moves and then scans the entire living room and models all the chairs and the drapes and the houseplants and figures out where to go next, right? Doesn't really make sense for something like Roomba. Okay. Okay, so that's sort of an embodied approach to planning. So we've gone through 3 different building blocks of cognition. We're going to see a lot more when we continue on with evolutionary robotics, but hopefully by now it's enough to sort of show you the different approaches that embodiment or non-embodiment gives to intelligence. Okay, so what actually is embodied cognition? If we want to try and boil this down to a simple sentence, simply it's just that you have a body. You could argue that this old desktop computer up here also is embodied. It has a body, it just happens to be this black rectangle. However, a traditional desktop PC cannot use its body to push against the world and observe how the world pushes back. So in contrast, the Lego Mindstorms robot over there on the right also has a body. It's inside a physical thing. The important difference between the Lego robot and the desktop PC is that the Lego robot can use its body to push against the world and observe how the world pushes back. That's what an embodied agent is able to do. Okay. If you have a body that can move, not only can you push against the world and observe how the world pushes back, you usually get immediate feedback. The moment I move in my world, I immediately sense a change, in this case in my visual sense. Right? And that's going to be important later. Okay. On the other hand, computers, yes, they have a body, they have a physical body, and yes, they get information from the world, but it's sort of passive. They have to wait to get it from someone typing in information or packets arriving over the internet. Any non-embodied system is fundamentally a passive system. It has no body, so it can't impact the world. It's got to wait for stuff to come to it. If you have a body, you can go out and get the information you need from the world to do whatever it is you're trying to do. Okay, that's embodied cognition. There is a related idea called situated cognition. And this is the idea that you are situated in the world, so similar to embodied cognition. But in situated cognition, the way that you process information is affected by the fact that you're physically situated in the world. So what does situated mean? It means that I am getting information directly from the world on my senses, right? So I have senses, a machine has sensors, information is coming in real time. So a simple example of that is an embedded device. So over in the Davis Center, if you go into one of the rooms and you're the only one in there and you're quiet, you don't move for a while, the lights will turn off, right? So there's a sensor sitting in the ceiling that's sensing movement and sometimes sound. And if there isn't any for a while, it will switch off the lights. That sensor is not really embodied. I mean, again, it has a body, it has a plastic casing, but it's not using its body. It's just sitting there, but it's situated in the world. It's in the world along with you in the sense that it's sensing something about the world in real time. Okay. So there's an example there. Again, a computer can sense in the sense that it can sense an incoming packet from the internet. But again, it's not really sort of a direct connection with the world. It's not sensing physical phenomenon directly like organisms do. Okay. Another way to think about this is if you're embodied, you have a body and you can use it. If you're situated, you have sensors and they're not filtered. Raw information is coming in real time. Okay, if we consider an agent, and throughout this course we're going to use this term agent as sort of a catch-all term for an organism, a robot, or a machine. A complete agent is both embodied and situated. It has a body to push against the world, and it has sensors to sense how the world pushes back. Okay. The minute you start to think about an agent that has a body and can sense repercussions of its actions, there are interesting properties of complete agents. And if the complete agent happens to be a robot, we can program that robot or evolve that robot to exploit some of these properties. So a big part of what we're going to see as we go through this course is how evolutionary algorithms exploit certain properties of complete agents to get them to do whatever we want those robots to do. So let's have a look at some of these properties and then just sort of think about how humans exploit those properties. Okay, so if you have a body in the world, then obviously you're beholden to the laws of physics, right? Unless you collect a machine that allows you to work against them. So as I move about in my environment, obviously gravity is acting on me. I'm a biped, so as I walk, every once in a while, one foot becomes the stance foot. So I rest my weight on that foot. The other foot lifts off, and that leg has mass. So what happens to that leg? So stance foot, stance foot, stance foot, and the one that is off the ground, it has mass. I can't help that. It's going to be acted on by gravity. What's going to happen to the leg that's just come off the ground? Any ideas?
Well, it's going to get tired because it's going to want to come back towards the ground.
It's going to want to come back towards the ground, right? So if you think about it, your swing foot, which is what we call it the moment it comes off the ground, what does it do? It's tired. You've just expended a little bit of energy to swing over it, and now it's going to start to swing back, right? Gravity is going to pull on your leg, and your leg basically becomes a pendulum the moment it leaves the ground. Now you can work against the laws of physics. You can tense the muscles in your swing leg, and it will not swing forward. But what you cannot do is stop gravity acting on it. You can fight against it, but not cancel it. Okay, seems a little strange. We'll come back to that in a moment. The moment that an agent uses its body to move about in the world, it generates sensory stimulation. So again, it's active. So this doesn't happen in this classroom, but if you're sitting in a classroom that's completely flat, from my perspective, those of you that are sitting in the back, actually it does work. Some of your faces are occluded. I can't see your face, but there's a simple solution. I can move, and now I can see you, right? So again, this seems in introspection and retrospect something that is so obvious, right? If there's some information you need from the world, you can get it by moving or acting on the world. If a deep learner is trying to learn about human faces in photographs, it can't go get those photographs. It might send an email to the investigator saying, I need more data, but it doesn't have a body to go out and get what it needs on its own. Okay. As we move about in our environment, we also affect the environment. We leave an imprint on that environment, and we may make use of it or we may not. But again, it's sometimes hard to not impact our world as we move about in it. The example I wanted to draw today usually works well in January, but not today. It's a little too icy. Immediately after a snowfall on campus and after first class, what starts to happen? You're late for your class, you slept in, you've got to get to your class. What do you need to do?
Move.
You need to move. How are you going to get to your class? In a hurry, hopefully, if you're running late. If you want to get there quickly, assuming you're not going to drive.
Run.
You're going to run, okay. And you're probably going to choose the shortest path, right? You're late. And you're probably not the only one who's running late, so there are other students that are pouring out of the dormitories that are also making a beeline for class. So after a fresh snowfall by about midday on campus, what happens? If you're to take some drone photography of campus,
There's going to be trails everywhere of people traveling.
there's going to be trails everywhere in the snow, but these trails are not arbitrary. What can you tell me about this network of trails that will reappear in the fresh snow?
They're probably somewhat linear and going towards class.
They're somewhat linear and going to, obviously, all the buildings on campus.
They're also going to be weighted, the most traveled ones, between the most popular places on campus, like leaving the dorm and then going to the rooms that have the most classes in them.
Absolutely. So we have a whole bunch of complete agents, you all, right, that are trying to get to class as quickly as possible. And as you do, after a fresh snowfall, you're leaving literally imprints on the environment, and they're not arbitrary. They become a network of shortest paths between the major buildings on campus. Obviously, you're all juniors and seniors. You know what all the shortest paths are by now, but you're also leaving clues for new students on campus who may not know. They might just follow the paths and figure it out on their own. So we have this impact, and other complete agents can exploit that fact. They can follow shortest paths between the major buildings on campus. This might sound like a little bit of a contrived experiment, but there is another non-human species that makes use of this fact all the time. Anybody know what species I'm talking about?
Ants.
Ants, and we'll come back to that with pheromone trails, not trails in the snow. Okay, so my leg, as I'm bipedally walking about, the swing leg, because physics acts on it, it will start to pull on it, and my brain can exploit that fact by relaxing the muscles in my swing leg. So instead of actively tensing the muscles and pulling my swing leg forward while I'm walking, I can relax all the muscles and let gravity do the job for me. I can sort of shut off the muscles and save a little bit of energy. As we'll see when we get to bipedal locomotion, getting a two-legged robot to walk is very difficult. But if you can, there's a lot of advantages because it's exceedingly energy efficient. So on half a Big Mac, you can travel 20 or 30 miles. If you're in good shape, you can travel 20 or 30 miles on the energy content of half a Big Mac. From a robotics point of view, that is an incredible feat of engineering. Bipedal locomotion is amazingly energy efficient because we have an embodied agent, and evolution has figured out how to exploit the physics of bipedal locomotion to make it very energy efficient. Evolution is exploiting properties of a complete agent. Our brains have also evolved to exploit the fact that we can move to generate the sensory stimulation that we need in a given environment. And evolution can exploit the fact that if there is enough of us, we collectively have an impact on the environment, and the signal or the signature that's left on the environment by embodied agents moving through it can often be, again, exploited. Okay, so we're finishing up lecture 3 here. So just to recapitulate here, let's think about this table for a moment. We've talked about different kinds of technologies already in this class. Humans, non-human organisms, where do they fit into this table? What examples have we seen so far of either technologies or biological systems that both lack a body and are non-situated?
It's a regular old desktop computer.
Desktop, the poor misaligned, maligned desktop computer, right? It has no body to act against the environment, and if there's no webcam, it doesn't have any way to sense the world directly, right? It's got to wait for packets to come to it, or someone to type on the keyboard. So a traditional computer would be an example of a disembodied and non-situated machine. What about a situated and non-embodied machine? You can sense the world but not really act on it very well, or in a limited way.
Something that senses the light level in a room or how much noise is in a room.
Exactly. So an embedded device, something that's embedded in the ceiling or embedded in the world and is sensing something about the environment. It has no body to affect the world. It can, in the trivial sense of being able to switch the lights on and off, but kind of a limited way of impacting the environment. Okay, bottom right corner, this one should be pretty easy. Examples? Us, humans, every single organism on the planet fits in that box. What about Shaky the robot? It's not the most sophisticated machine, but Shaky can move. When Shaky moves, the world around it changes. It's both embodied and situated. So autonomous robots are definitely examples that fall in the bottom right. The top right box, embodied but non-situated. This is a little trickier.
Maybe something like an RC car, something like that?
An RC car.
Yeah.
I think so, right? Yeah, as long as it's not sensing the world, it has a body, it's definitely driving around. Yeah, that would be a good example. Other examples? We've already seen an example in class already, last week. No. The first generation of industrial robots that we saw back in the 70s, most of them didn't have sensors on them. The robots, or the builders of the robots, assumed that the environment that they were in was going to be so completely structured that the robots didn't need to sense the environment. So the industrial robot welder that's welding the door of a car, it would just blindly do it at a certain frequency with enough time for the new car door to arrive just as the welding iron reaches the door. So the early industrial robots could get away without sensors, which made them cheaper to build, which was good news. Could be embodied but non-situated. But obviously it's not an ideal situation. If you have a body and you're impacting the world and you can't sense the repercussions of those actions, not a good situation to be in. Okay, hopefully this table helps you remember the difference between embodiment and situatedness. Okay, any questions about that before we move on to lecture 4? All good? Okay, so now we're going to move on to tools of the trade. You've already started on physical simulation by building your empty PyroSim simulator. So we're going to run ahead a little bit and talk first about artificial neural networks, and then on Tuesday we'll get into evolutionary algorithms. To structure our discussion of neural networks, we're going to start with some familiar friends by now, hopefully, Bradenberg's aggressor and coward. And we're going to do something a little bit taboo. We're going to take these nice embodied agents and make them non-embodied. We're going to throw away the body for a moment. We're going to build up their brains, and then we're going to put their brains back into their bodies. All right? Okay. So, as you remember, the Bradenberg vehicles have 2 sensors, they have 2 motors, and they have 2 wires connecting the sensors to the motors. So in the top right panel here, we're going to, again, throw away the body. And for now, those 2 top circles represent sensor readings. And the 2 values arriving at the output layer are going to be the values that we send to the motors. In the case of the Bradenberg Series 2, the inputs are what? What do those values represent? They're coming from the 2 light sensors. So what do the values represent?
The intensity of the light.
The intensity of the light, right? So in this little cartoon in the top right, there's more light falling on the right sensor than the left sensor. What about the values arriving at the output layer? What do they represent?
Speed off the rail.
The speed of the wheel, right? How quickly we want the wheels to spin. The next moment, when the input layer changes, the output layer is also going to change, and the wheels are going to spin faster or slower. In assignment 2B this week, you're adding joints to pairs of objects, which connect those pairs of objects together. And that joint, when we actuate it, or we attach a motor to that joint, can pull or rotate the two objects closer to one another or rotate them apart. Same thing. Those values are going to represent how quickly or in which direction we want to rotate the two motors, the two objects relative to one another. Okay. The little pluses that you see in Bratenberg's cartoons here represent that we're just taking the value and passing it from the input neuron to the output neuron. Nothing too complicated going on here. Of course, we don't have to connect just one sensor to a motor. We can connect arbitrary subsets of sensors to arbitrary subsets of motors. So in the bottom left, I've started to add some additional wires, which are not actually wires, but they are synapses. So synapses in biological tissue are the connections between neurons. They pass signals from one neuron to the other. Our synapses here we're going to represent as these lines that pass signals from sensor neurons to motor neurons. Okay, so pretty simple. If we have two or more incoming connections to a neuron, we simply, and now you can see what the plus means, we're simply going to sum the values. So this motor neuron here is receiving 0.6, 0.6 plus 0.9 is 1.5, pretty straightforward. What would this robot, or what would this network in the lower right do if we put it back inside a Bratenberg vehicle? Assume that these are still light sensors.
It's always going to go in a straight line.
It's always going to go in a straight line, right?
Where you put the line, it only depends on your initial angle.
Absolutely. So this robot can no longer turn, but it can go faster and slower, right? It'll go faster if there's more light in general. It'll go slower if there's less light. So we've made a change from the top right to the lower right in the cognitive architecture of the robot's brain. So cognitive architecture is just a fancy word for we've changed the wiring inside the robot. And by changing the wiring, we've changed the robot's behavior. What we're going to see in most of the evolutionary robotics experiments in this course is some version of that. Evolution makes some change to the wiring and observes the change in the robot's behavior. If the change is for the better, that robot survives. If the change is for the worse, that robot is probably not going to survive. Okay. Let's make another change. So at the moment, we've just taken the value of an incoming neuron and added it to the value of the output neuron. We're now going to throw these plus signs away, and instead we're going to assign weights to these synapses. For our purposes in this class, these weights can be positive or negative floating point numbers, and they represent the weight of influence of this neuron on that neuron. So instead of saying this neuron and that neuron, I'm now going to start to talk about presynaptic and postsynaptic neurons. Pre- and postsynaptic neurons. So for a given synapse, this synapse has two neurons associated with it. The presynaptic neuron, which is where the value is coming from, and the postsynaptic neuron, which is where the value is going to. Pretty straightforward, right? Okay. So the weight of a synapse indicates the weight of influence of the presynaptic neuron on the postsynaptic neuron. Okay. A weight of 0 means that the presynaptic neuron has no influence on the postsynaptic neuron. It doesn't matter what the value of the presynaptic neuron is. We're going to take that value and multiply it by the weight and add it to the raw sum arriving at the output layer. So this is the magic formula in almost all neural networks, is we visit each neuron in turn and we consider all of the presynaptic neurons of this postsynaptic neuron. This one has 2, that one and that one. And we take the value of the presynaptic neuron, multiply it by the weight of the synapse, down here, and then go to the next presynaptic neuron, take its value and multiply it by the weight of its synapse, and calculate that raw sum. So a presynaptic neuron has two different ways of influencing a neuron. Its synapse might be strong negative or strong positive, and the actual value of the neuron, of the presynaptic neuron, influences the postsynaptic neuron. So far, so good? Okay, so as we're going to see, again, evolution can make changes to the wiring or the cognitive architecture of our robots by adding or removing or changing synapses. Evolution can also make changes by leaving the wiring intact, but fiddling with synaptic weights. Okay. So that's synaptic weights. However, we can see now that the raw sums that are arriving at the output layer have very different magnitudes. One is 0.09 and one is 1.29. So for various reasons, which we'll get into later, we also usually add to our neural networks an activation function. And activation functions live at the neurons. Synaptic weights obviously live at the synapses. Activation functions live at the neurons. And what an activation function does is take as input the raw sum and pass it through a certain function that will squash the raw sum down to lie within some predetermined range. In the work we're going to be doing here, we're going to arbitrarily set the predefined range to be between -1 and +1. So all of the neurons in your simulated robots, we're always going to know what range they lie within, between -1 and +1. Question? What is the point of that? Is we want to make sure that they all have about the same range, and there's several reasons. One of the reasons is that remember that we're going to send the value of some of these neurons to the motors. They might say how fast we want the motor to spin, or how quickly we want two connected objects to rotate relative to one another. We'd like to have that range beforehand so that we can then scale that range to the allowable range for the motor, right? So you could get something like a value of 200 here if we're not careful about the synaptic weights, and we might tell the wheel to spin at 200 revolutions per second, and you'll burn out your motor within a tenth of a second. Okay. That's one reason why we do it in robotics. Yep.
Back on the formula.
Yes.
What happens if x is equal to 0 or 1?
So you're looking at the one in the top right,
Yeah.
right? So this is with the threshold one. I'm sorry, so say that again.
What if x is equal to 0 or 1? Because they're all greater than or less than, so there's no greater than or equal.
You're absolutely right. There's a mistake here. So this should be less than or equal to, and this should also be less than or equal to. Good catch. Exactly. Another thing here is the example I gave you here. This is when we're squashing the value to between 0 and 1. But remember, we're really doing it from -1 to +1. It doesn't matter too much what the range is, because we're then going to scale that range back to the allowed range of motion of the motor. The point I want you to just take away from the activation functions for now is we're taking these raw sums and squashing it back to some desired range. There's different functions that we could use to do the squashing. A common one in the literature on robotics and AI is the sigmoid function, which has this nice smooth surface, which means it's differentiable. Doesn't matter for our purposes, but in other branches of machine learning, it matters. So we're going to use this activation function. And now we're going to take all these pieces and we're going to apply them to some example neural networks. Okay. One of the nice things about neural networks is at heart what they are is just a way of representing a function. They're a function in the sense that they take as input a vector, which in this case is a 2-element vector. And in this cartoon example here, they transform that vector into a scalar. If we go back to our 2x2 here, we take a 2-element vector and transform it into a different 2-element vector. Okay, so since neural networks encode functions, we can actually take a function and encode it as a neural network. And by doing that, it's useful because you start to build up an intuition for how these neural networks start. So let's start with a very, very simple example. Let's start with a truth table. Let's imagine we have two inputs to our neural network. And we're going to assume now that these inputs are binary, either 0 or 1. And the output is going to be either 0 or 1. So I just finished telling you we want neurons between -1 and +1. For the next couple of cartoon examples, we want the range to be between 0 and 1, because we're going to do some Boolean logic here. Okay, so if the two values arriving at the input layer are 0 and 0, we want an output of 0. If the values arriving at the input are 0 and 1, we want an output of 0. If 1 and 0 is input, we want an output of 0. If both are 1s, we want an output of 1. Hopefully this function should be very familiar to you. What is it? It's the AND function, right? So we're going to encode the AND function in a neural network. We're going to use a threshold activation function over here. We have just one output neuron, so we only need one activation function for this neuron. We need to pick one number in here, which is going to be the threshold. If the raw sum arriving at this neuron is above our threshold, we're going to set the output to 1. If it's below the threshold, we're going to set the output to 0. Okay? You also have to pick a second and a third number, which are the synaptic weights of these two synapses that connect the two presynaptic neurons to the one postsynaptic neuron. Turns out there are many triplets of numbers that will instantiate the AND function. What are some of them? Any guesses? What do we need to set the two synaptic weights? And what threshold do we need to set to make sure that if 0 and 0 arrives, 0 arrives at the output, and so on?
You have to set them both to something between 0.5 and 1.
Okay,
Exclusive.
okay, so let's pick one. Let's set them to 0.5, right? Doesn't really matter. So we're going to set the weights of both of the synapses to 0.5. And now what do we need to set as the threshold for our activation function?
1.
1. Okay. So let's go through and do this. 0 times 0.5 is 0 plus 0.5, which is 0. 0 plus 0 is 0. 0 is less than 1. 0 is less than 1, so we set our output to 0. Let's go to the second row in our truth table. 0 times 0.5 plus 1 times 0.5 is 0.5. 0.5 is still less than our threshold, so we set the output to 0. So 2 out of the 4 rows are good. 2 out of 2. I won't do the third row because it's the same. Let's do the fourth row. 1 times 0.5 plus 1 times 0.5 is 1, which is, I guess this should be greater than or equal to. Actually, let's make things easier on ourselves. Let's set the threshold to 0.9. 1 times 0.5 plus 1 times 0.5 is 1. 1 is greater than 0.9. So we set the output to 1. So if the two synaptic weights are set to 0.5 and the threshold is set to 0.9, then that neural network encodes the AND function. So far, so good? That's the AND function. Let's try and do the OR function now. So we still have 4 cases to deal with. But now we want to make sure that we get an output if one or both of the presynaptic neurons is set to 1. What are we going to need for our weights, our 2 weights, and our threshold to make this work now?
Keep the weights at 0.5 but lower the threshold.
Okay.
Like 0.4 or something.
Exactly. So we want 1s to occur more often, so just intuitively we're going to reduce the threshold. What do we need to reduce it below?
Well, 0.4 would work, but less than 0.5.
Okay, let's set it to 0.4. So 0 times 0.5 plus 0 times 0.5 is 0. 0 is less than 0.4, so the output is 0. Let's go to the second row. 0 times 0.5 plus 1 times 0.5 is 0.5. 0.5 is greater than 0.4, so we got above the threshold, so we set the output neuron to 1, and I won't do the third row and the fourth row, but you should easily be able to see by visual inspection that this weight and this threshold instantiate the AND function, or sorry, the OR function. So again, these are two very simple examples, and you don't need to memorize them or remember them. What I want you to take away from this is that, again, we've made a change, in this case to the activation function. We've made a change to a part of the neural network, and by doing that, we've changed the function that the neural network computes. We changed it from computing the AND function to the OR function. When we put these neural networks back in the robots, the neural networks are still computing a function. They're taking the robot's current sense of the world, they're taking all the sensory information the robot is getting at that point in time, and transforming that sensory information according to some function, and that function is going to be set by evolution. Evolution is going to tinker with the synaptic weights, and in some cases the activation function, and it's going to then output new values to its motors. Every time evolution makes a change to the neural network, it's making a change to how the robot transforms its view of the world into action. So far, so good? Okay, let's try one more. The XOR function, which, as the name implies, exclusive OR is the same as OR, except for the fourth line. If both incoming neurons are 1, output should be 0. How do we set the two weights and the activation function to instantiate the XOR function? Tricky. This is actually a trick question. Why is it a trick question?
You need to have 3 functions instead of.
You can't do it. There is no setting. If we stick to the real numbers for weights and activation functions, there's no triplet of real numbers that will encode the XOR function.
Could you not use negative weights on the synapses? So if it was a negative, if it was scaled to be negative, then we could see if it was XOR.
You can try. It still won't work, and we don't have time today, but you can try with pen and paper. And if you manage to get it to work, please let us know. Remember, there's a Nobel Prize waiting to be won in this field that could do it. That could do it. Okay, so we are going to have to add, there's no setting of the weights or activation function, so we're going to have to make a more fundamental change to the cognitive architecture. We're going to have to add not just more synapses, but more neurons. So we're going to add the last piece of neural networks that you're going to need for this course, which are hidden neurons. Why are they called hidden neurons? Well, they're hidden or sandwiched between the input layer and the output layer. And again, if we imagine that this neural network is sitting inside of a robot, these hidden neurons are sort of hidden from reality. The input neurons, at least, are getting information directly from the real world, and the output neurons are directly influencing the motors, but the hidden neurons are the middlemen of the neural network world, right? They don't directly affect the world. They transform, or they help transform inputs to outputs, but they're hidden in the middle. Okay, now, I do promise you that with this cognitive architecture, you can realize the XOR function. A little bit more tricky. So I made this little template for you to annotate, and what you're going to need to do is put in 3 different values for activation functions. So each of the 2 hidden neurons and the output neuron, each of these 3 neurons needs its own number, its own threshold, and we also need 1, 2, 3, 4, 5, 6 synaptic weights. So we need a total of 9 numbers. I'm going to give you 2 or 3 minutes to try this out on your own. If you want to turn to your neighbor and try and work it out together, that's perfectly fine. When you get your 9 numbers and you pass them through the neural network, it should produce this truth table. I've also given you this little arrow here, so a good way to write this out is to try and sketch it out and figure it out. Put the raw sum over here, take the raw sum, compare it to your threshold, and either write a 0 or a 1 here if the raw sum is below the threshold, and write a 1 if it's above the threshold. See how you can do. I'll give you 2 minutes to see if you can figure it out. Okay, as I mentioned last week, creating these neural networks by hand is exceedingly difficult. This is part of the reason why we try and automate this process. Now, before I ask anyone if they found a solution that they think works, there is a general strategy to try and solve this problem, which is, if you look at this picture, you'll notice that each of the two hidden neurons, you can think of these hidden neurons as computing a sub-function. They compute part of the solutions, and if they compute part of the solutions, you can then combine the solutions together at the output layer. So have a look at the two input neurons and then just one of the output neurons. Looks a lot like this. What's a general strategy for solving this problem?
I would do both the hidden ones as and then do a not or for the last one.
Okay, so we could try and set the two hidden, we could set the two synaptic weights and the activation function threshold to instantiate the AND function. We know we can do that with two presynaptic neurons and one postsynaptic neurons. And we could get the second one to also compute an AND.
No,
Not an AND.
a not or.
We could try and get it to do a not or. Can we compute a not or in this way? We could do that. There's a simpler solution. You're on the right track. We're going to get each of these two hidden neurons to compute a simpler logical function and then combine their results. What are the two subfunctions we're looking for? AND is one of them. Any ideas? Or, right? So we're going to, I won't go through it for now, but let's assume we write down the synaptic weights and the activation function so that the left hand hidden neuron computes and the right hand hidden neuron computes or. How do we need to combine those results?
Would you have to have the two that cross, they would have to be slightly lower so that combined they create the paradigm?
Possibly. So don't worry about the cross connections up here, right? Let's assume we've solved all those. We've set the synaptic weights for those four synapses at the top, and we've set these two activation functions. So one of them does this, and one of them does this. We got that piece. So we've got these two neurons down here computing the and the or function. How do we combine them so that the output neuron gives us the XOR function? Have a look at the truth table on the right. The first three rows, right, are exactly the same as or. First three rows are the same as or. So we kind of want to let those through, so to speak, in three cases. But in the fourth case, We don't want the OR function to go through because it's wrong. We want to somehow suppress the OR function, but only in this fourth and final case. How do we do that? We're thinking now about just setting these two synaptic weights and this activation function threshold here.
Be another OR.
Maybe. Let's think about the suppression for a moment.
You have the left one be negative and the right one be positive.
You got it, right? So the left one is computing the AND function, and the right one is computing the OR function. So let's at least label this with a 1. We're just going to let the OR function come through. This one is computing the AND function. And remember that the AND function only lights up in the fourth and final case, right? 0, 0, 0, and then 1. So only in the fourth case is this AND neuron going to change from 0 to 1. The moment it does, we're going to multiply it by a negative synaptic weight, right? 1 times minus 1 is minus 1. So there's a 1 coming here in the fourth case. There's a 1 that's flowing down this line coming from the OR function. And now there is a negative 1 flowing down from the AND neuron. It's going to cancel it out. Remember, we do the raw sum, right? Minus 1 plus 1 is 0. So what's the threshold we want to set here? So minus 1 plus 1 is 0. And we want to make sure that the final output in this fourth case is 0. So we're going to just set the threshold a little bit above 0. 0.4 will be fine in that case. The rest of the time, so in the second and the third row, that's the OR function, right? So the OR neuron here is sending a 1 down this line, and the AND here is silent, right? It's 0. 0 times minus 1 is 0. So in the first 3 rows, there is 0 suppression coming from the AND neuron. It's only in the fourth case that the AND function slams on the brake and says, oh no you don't, OR function. You're not going through to the output layer. I'm going to cancel you out and get 0. So I've been mentioning suppression, but in the neuroscience literature, this is just known as inhibition. So a synaptic weight that is negative indicates that the presynaptic neuron is trying to inhibit the postsynaptic neuron.
I'm just curious why that's better. I mean, the solution that I came up
Okay.
with was 0.5 on the input ones,
Okay,
and an activation of 0.9. So and on both cases, and then the next.
it's got to be
one-
and something else, right? It can't
Well-
be and on both cases. You can't, because then it's redundant. And you
Okay.
said not or, I think, right?
Well, right, and then on the last one, you put negative 0.5 for your weights, and then,
Okay.
and then the activation function of like negative point 0.6 or something like that.
That's possible. That could be a possible solution as well. So as we saw in the previous examples, there are multiple sets of weights and activation functions which instantiate the activation function threshold that instantiate the same function. That may work, actually.
Okay.
That's fine. That's fine. Okay, so I've written them all out here for you. So actually we have the AND function over here that's suppressing the output layer, and here's our OR function. You can recognize that this is the OR function because it has a lower threshold, right? It allows more things to go through, right? It's more forgiving. There's the AND function over there that's less forgiving. So we have 2 hidden neurons that are computing subfunctions and then combining those subfunction results. You'll remember last week I talked very briefly about deep learning networks that took as input a set of pixels and tried to output at its output layer whether there was a human or a cat or neither in the photo, right? They work in sort of the same way, right? That we're computing these subfunctions as we flow, in this picture here, from the top to the bottom, right? And we're computing these hierarchical subfunctions and then combining the results of these subfunctions together into more and more global results. Yes?
Does each neuron have to use the same activation function?
It does not. So you can see in this case, the three neurons each have different, they have different thresholds. They have the same activation function.
Yeah.
They do not have to have the same activation function. We could ask evolution to set synaptic weights and choose one of these four functions for each neuron. You could do that as well. It's a good question. Okay, so again, you don't need to memorize how these neural networks encode these different functions, but you'll notice that certain neural networks are not able to compute some functions. We had to add some additional neurons here to allow, in this case, our neural network to compute a nonlinear transformation. Why is this nonlinear? Well, if you sum the inputs on each of these rows, you can see the sum of the inputs is going up. 0, 1, 1, 2. And the outputs go up, and then they go back down again. It's a nonlinear function. Why does this matter? If your robot does not have hidden neurons in it, then there are only certain transformations it can perform on its sensory input. In other words, there's a subset of ways in which it can react to what it senses in the world. If we add 2 hidden neurons into our robot, we give it greater flexibility, we give it greater behavioral flexibility. It can react in a larger number of ways to what it senses in its world. And again, we'll see cases of that as we go. Okay. So as I mentioned, there's this large field of machine learning, and the backbone of the whole field of machine learning is this idea of backpropagation. And again, I'm not going to go into the details of this. We've got 5 minutes left. We'll finish with this. Imagine we have now a supervised learning task, which I mentioned already. Why is this a supervised learning task? It's supervised because we know for any given input what we want the output to be. So in this case, let's imagine we've taken these 2 inputs, applied it to the input layer, we've propagated it down. I'm not writing the activation function here. Doesn't matter for our purposes. Imagine that this particular neural network outputs 1 and 1, but we wanted 1 and 0 as the output. So the first neuron was correct, error 0. The second neuron was wrong. So we're now going to go in and fix the synaptic weights to fix this local error. One part's right, one part's wrong. So what do? We start where the error occurred, which was that lower right-hand neuron, and we propagate backwards along the incoming synapses. So you can see all of the arrows that point into that erroneous neuron. I've turned them red. We've traveled back along them, and we've changed the weights. And I'm not going to go into the details about how we change the weights. But we changed just those weights to switch the output of just that neuron until it's correct. Now it's correct. Both of them are correct. We're done. So we're making, in backpropagation, the beauty of the backpropagation algorithm is we're making localized changes to the network. We're isolating where the error occurred and then trying to fix things nearby. So this is like using tweezers on a neural network. Some parts are working, some aren't. Go in and fix them a little bit. Question?
So do you just go like one layer back, or do you go all the way back?
You go all the way back, and you often go back and you change things less as you go further back. There's 1,000 variations of the backpropagation algorithm. I want you to just take away the intuition of how it works. Okay. One last thing. One of the problems with neural networks is they often overfit. So I already mentioned this last week, I think. As we just saw, sometimes you need to add hidden neurons to get the neural network to do what you want. But if you add too many, what happens is often the neural network will overfit. So imagine we now have the data table you see on the right. It is still a truth table. We now have more inputs. So we have k inputs, and each input is going to correspond to whether a given patient is registering a given symptom or not, yes or no. And the output neuron is whether they are manifesting a disease of interest or not. So we're going to now try and train our neural network to take as input patient N+1 and their symptoms. And the neural network is then going to output a prediction about whether that patient is suffering from that disease or not. Okay. If we have, let's imagine we have N patients in our data set, and we have N hidden neurons. What can happen is that when we train our neural network, the subfunctions at each of these N hidden neurons is not and or, it's a patient recognizer. So hidden neuron 1 says, don't worry guys, I'm going to memorize the symptoms of patient 1, and I'll then set my output to be whether they had the disease or not. Hidden neuron 2 says, I'm going to memorize patient 2. I will only turn on when patient 2 is present at the input layer. And my synaptic weight will indicate whether the patient 2 suffered from the disease or not. So what's actually happening here is the neural network is memorizing each of the patients and whether they suffered from the disease or not. And if we supply any of those N patients, this neural network will get it perfectly right. So we can get a neural network to get perfect zero error because it's memorized everything. But if we come along with a new patient that has some combination of symptoms that doesn't exist in the initial N patients, how is that neural network going to do?
Well, it doesn't recognize any of the specific patients, but it's probably gonna tell you very confidently that it is close to this person.
Possibly, right? So it's going to try and take a guess, right? Maybe it's close to this patient, so maybe this, right? If you memorize last year's exam and the professor gives you a different exam this year, you may do well, you may not. Okay, I think on that note, we'll leave things there. You have a quiz due tonight, and you will be finishing up assignment 2 for next Monday night. Have a good weekend.